Okay. Is the desktop there? Can you hear me and see me? Anybody there? Huh.
Yes, we're here.
Pardon me? Yeah. Okay. So you can see me here, or you can see the desktop and hear me, right?
Yes.
Okay, great. Thanks. Okay. Um, okay. So last time we managed, let's see. I think we pretty much this was the code we were working on last time, and I think we went through all the code. You know, yeah, remember we got the final fastest code to search through this this 2 GB file was
4 seconds.
remember the idea was to interleave, to find a nice interleaving of the IO step with the compute step, to get them in this kind of balanced state here, not in this lopsided. And it worked when with a fairly good size buffer, and the IO part just read one buffer and immediately passed the whole buffer to parallel task. Okay, so the parallel task just did each parallel task did one whole buffer with many lines in the buffer. And remember, it was a little bit quirky. To keep track of where we were in the file, we have to count lines here. And then we also have to count lines down here too. Yeah. Now, I mentioned that it's not that unusual in parallel code where you have to do redundant work, because both this task needs to know what line number it's in within the buffer, but this overall thing needs to know how many lines were in the buffer so it can keep track of where we are in the whole file. So that's kind of weird that it ends up being faster, even though we're doing a little bit of redundant work. It still ended up being pretty fast. Let's see. That's the version that read from standard in. This is the one that just read from the file, and yeah, it's pretty quick. It finds it searches that whole file in just about 4 seconds. Okay. All right. And now what we're going to do now is switch to the processing the 1,000 files. Remember, this file here is really 1,000 files concatenated together. Okay. So I want to switch to working on the 1,000 files themselves. So got them in a different folder. And I realized I should also, on the website, I put a link to Andrew's original collection of 40,000 files. Then here's the link to my concatenation of 1,000 of them to get this 2 GB file. Now I'm going to switch to using the 1,000 files, and I should I'll compress these 1,000 files. Here's the folder one, because you don't know which 1,000 files I use. So if you want to duplicate what I'm doing, I need to give you exactly these 1,000 files, because I filtered out some that were that had bad data in them. So it would be really hard for you to figure out which 1,000 files I've actually got. So I'll compress these 1,000 files together and give you a link to that too. So then you'll have the original collection of all the files, the 1,000 files concatenated and the 1,000 files individually. And you can try duplicating this code. Okay. Now, the first thing to do is just to look at a little bit of code that just like how do you go through all the files in a directory? Okay. So here's a little program, just a couple lines, that's going to list all the files in the directory. Okay, so this line of code, this one line of code here, well, and this is kind of neat. This is using really ultra modern Java. I was looking in a book and I found some examples of very nice modern Java. So this is using streams. So you create, there's a static method in something called the files class that will create a stream of all the paths in the current directory. So this guy returns a stream of all the paths in the current directory. Okay. Then for each path in that stream, I call the print line method. I don't know if you've ever seen this notation here. What I'm doing is I'm not calling a method, I'm passing a method. I'm passing this print line method in the system.out object. I'm passing that method to the for each function. Then the for each function will apply that method to each object in this stream. Okay, it's a really modern style of Java programming. You write one line that replaces 10 or 15 what would normally be 10 or 15 lines of code. So, and we're using pretty high level libraries here that are fairly new, but that work pretty well. So the list function returns a stream of paths, okay, and it returns the stream of the paths in the current directories. Then for each one it prints it. So if I compile this and run it, it lists the 1,000 files in that directory. So now I have a way of getting at the 1,000 files in that directory. But I only want to process the ones that end in .txt. So here's a little trick. I can take this line of code and put a filter in the middle of it. So after I get the stream of all the files in the directory, I filter that stream with a lambda expression. The lambda expression takes a path and it applies this, this is the lambda expression. It applies this little, it's a little one-line function, Boolean function. So one-line Boolean function. For each path in the string, it takes the path. For each path in the stream, it takes the path, converts it to a string, and then checks if that string ends with .txt. So I'm looking for the files in the current directory that end with txt. So I take a path, convert it to a string, then use the ends with method on the string. If this is true, then that path is passed to the next stage of this pipeline. These are actually pipelines. Okay, so I put a filter in the middle of the pipeline to filter out the paths that don't have txt at the end of them. Okay, then for each path in the filtered stream, I print out the name of the path. Okay, so if I run that, I only now have the, I've now filtered out all the other files in the directory that are like the C programs, the Java programs, anything else. Okay, so there's the approximately 1,000 text files in the current directory, /name of the file. Okay.
Question.
Yeah.
Other than like illustrating these super cool and modern Java facilities that we now have, why do this part of the program in Java? Like, this is best done in a shell, what you're doing right there.
Because the Java program needs all those directories.
Well, I know what you can just pass it to Java through the shell rather than having Java do it
Well,
itself.
there's not clear which is really better. So if you're writing a really large 10,000 line program, do you really want to say, oh, at this point, you're supposed to drop into a shell and have the shell list out all the files in the current directory and then pass them through a command line to the Java program? The Java program should, within itself, be able to do anything. For example, who wrote the shell? If you think about it, why should a Java program break off and call a shell when the shell is just written in C or C++ or Java maybe even anyway?
I was thinking more the other way around. The shell calls the Java program. Have
But
the Java program
but
function over a single
but yeah,
file.
but you're not thinking of a large program, you're thinking of a little program.
Mm-hmm.
What if somebody has to write a large program that processes massive amounts of data on servers? You can't just assume that the large program is made up of little programs that a shell can call. And it's not even clear that that's efficient. That's convenient, but it may not be efficient. It may not be at all the fastest way to do things. So Java needs its own ability to get all the files in a directory and give you a way to get a list of them. You know, working with a shell might be more convenient in some cases, but it may not be in all cases. And even the shell, someone had to write the shell in something. So the ability of the shell to find all the files in a directory is because there's a library function that the shell was written in that knows how to do that. And here's the library function in Java that knows how to do that. So if you were going to write a shell in Java, you'd have to use this library function. Because otherwise, if you're writing a shell, the shell can't ask another shell to get into a list of all the files in a directory. So this is good practice in seeing what are the library functions that would be used, for example, to write a shell. Who knows how many files are in a directory? Who is
That
the
would be the operating system.
right? So yeah, the shell has to ask the operating system that question anyway. So these are functions that'll directly ask the operating system how many files are in this current directory. So these are Java library functions that will directly communicate with the operating system, just like the shell would have to do. Now, the shell would probably use the C library functions. More often than not, the shells are written in C or C++, so they would use C library functions. But if Java is well written, the Java library functions should be just as fast as the C library functions. Okay, the Java library functions would probably not be written in terms of C library functions. The Java library functions should be direct system calls to the operating system, just like the C library functions would themselves be direct system calls to the operating system. Okay, so yeah, in this case, we are going to do it all within Java. We're going to do it all from within Java and see how Java can process 1,000 files in a directory. Turns out to be unbelievably fast. I'm actually a little bit surprised at this. Well, the bottom line is when I switch from processing one big data file to processing 1,000 small files, the program ended up being just as fast. I was expecting it to actually slow down a lot, and we're going to see it didn't slow down. It slowed down maybe 10%. There was a little bit of a hit, and that actually surprised me. I mean, because in the past, I've seen many programs slow down by massive amounts when they switch from processing one big file to lots of little files. I've seen that over and over again. And I thought that was maybe now I'm starting to think that that's not a fault of the libraries, that's a fault of whoever wrote these programs. But it's not unusual to see a program have a huge performance difference between a 2 gigabyte file and 1,000 files that add up to 2 gigabytes. But I didn't see any performance hit here. So we'll go through. So I'm going to use this line of code over and over again now to process all the files in this directory. So like the first thing I want to do is count how many characters are in all of them. Okay, so remember here's a Java program. that counts all the characters in the data file. Okay, so this program counts all the characters in the 2 GB data file. Okay, you can compile it. This one doesn't time itself, so to time it, I need to open a command line. Okay, so that's count bytes in files. Oops, it's a Java program. So count the bytes in the okay, that's how many bytes. Okay, and you can double check. We're getting the right answer, are we? Yeah, we're getting the right answer. There's the number of bytes in the file according to the operating system, and there's how many we just counted. Okay, now I can time that. Okay, it read through that 2 GB file in under a second. You know, it took under a second to just in a very, it doesn't really read it reads every byte, but it doesn't look at every byte. So it reads the file buffer by buffer and just counts how many bytes were in each buffer. So it's just gonna, it asks the operating system to fill the buffer, then it just asks how many bytes are in the buffer. It doesn't scan through the buffer in any way, but it does make the operating system read every single buffer full of the file. Okay, now count all the bytes in the 1,000 files. Okay, so here's how we're going to do that. Here's how, it's just a slight kind of a little modification of that file. This is the trouble with working in a directory with 1,000 files. You have to keep scrolling through it. Okay, instead of count in file, I'm going to count in files. Okay, and what I'm going to do is, here's the fancy little piece of Java. And now, after I've got the paths and filtered them, for each one, I'm going to call essentially what was this, I'm going to take this thing, and this main method is going to be turned into a private method. I'm going to turn this main method into a method that just counts the bytes in one file. So I basically took this code and turned it into a function. And then I apply that function using a lambda expression. I call that function on every one of the paths that came out of the filter. Okay, so get all the files in the directory, filter out the ones that have txt at the end, then count the number of bytes in each file. And I have a global counter up here so that this guy can keep, he counts the number of bytes in the file, and then he adds them to the global counter. And this is the serial version, so I don't have any worry about race conditions. So this is just going to read a file, count the number of bytes in it. It'll keep track of the counter up here. Okay, and each file will be opened. Okay, each file will be opened, then it'll be processed. Okay, and it's the exact same code as was in here. Okay, so each file is going to get opened, processed, and then this thing will return, and then this guy will do the next. This guy will iterate. This will be the thing that iterates through all the files in the directory. Okay, and compile it, and then run it over here. Okay, there's the one that read the whole big file, but the one big data file. Now here's the one that reads 1,000 files individually. Notice they got the same answer because the big file was the concatenation of all the little files. Time them. Took about 0.8 of a second to read one huge file. It took just a little over a second to count 1,000 files. Not bad. I was expecting it to be a lot worse. I was actually expecting it to be a lot worse. So it's a little bit slower. It varies a lot from run to run. Sometimes when I ran this one, it would actually be just under a second. Sometimes it's just over a second. So there's the one that reads the huge file. It's pretty consistently just under 9/10 of a second. And here's the one that reads the 1,000 files. Yeah, it's just barely over a second. Okay, so at least the Java and Windows are pretty good at eventually we can go to the 40,000 files and see if it how well that keeps up. Okay, but 1,000 files is a fair number of files to have in a directory, and it read through the there's 2 gigabytes of data in this directory, and it read through 2 gigabytes of data spread over 1,000 files, and it read them real fast. Okay, so we're now able to process a large number of files in a directory. Okay, and a little bit of fancy Java up here, which is iterating through the files, and then the real more traditional Java that we've been writing down here that goes through and counts the bytes in one file. Okay, now the next thing to do is to do something with the files, not just count bytes in them. Okay, so let's do something more interesting with the files. Now that we can process, we can count the bytes in it. Let's see, what was the next one? Well, let's go to searching. Yeah, let's just go ahead and start searching. Okay, so first let's search in serial. Okay. Here's the sequential search. Okay. This one is the one we looked at the other day. This searches the 2 gigabyte file. This one searches through the 2 gigabyte file. Okay. See, it opens that file, I call it data. It just opens that file and searches through it and finds the aardvarks. And it runs reasonably fast. This was the fast sequential search. Okay, it took about 6 seconds. Okay, now let's do sequentially go through all the files in the directory. And I kind of did it the same way I did the other one. I took what was this main method and turned it into a static method by itself, and then just have the main method do the iteration through all the files and call this for each file. Okay, so that's this code here. Okay, it starts a timer, then there's the part that iterates through the files, and then it stops the timer. Okay, and says how long it took. And for each file, it calls search, it does search in file. Then the search in file here is almost exactly what the main method was over here. Not too much difference. Okay, so what it's going to do is it's going to open the file. Okay, then read the file buffer by buffer, look for new lines to keep track of how many lines are in the file, look for the aardvark. When it finds an aardvark, it'll say what line number it was in the file, and it's also keeping track of how many lines it's read through all the files. So it'll also tell us what line we are at totally. Okay, so there's this global line counter, like there's a global line counter now, and a local line counter for each file. Okay, and when you read through one file, at the end, you update the total line counter with the number of lines that were in that file. Every time you find an aardvark, you can report what line number it was, what file it was found in, and that's the line number in that file. And then this is the line number we are total as we've gone through the directory system. Okay, these numbers here should more or less match up these numbers here, because these files were concatenated together. All of those 1,000 files were concatenated, I think, in alphabetical order. So they were concatenated pretty much in the order that they are in this directory. Okay, so now you can compile this. And the interesting thing is, how does it compare, there's the result of going through the 2 GB file. And then here's the result of going through 1,000 files. Notice that performance-wise, whoops, what did I do? It's actually a little bit, this time it was actually faster. It actually beat the sequential reading. It beat the one where you just read through the file by itself. Okay. Okay. The line numbers are not quite adding up. There's a little bit of offness in the line numbers. I think when the files got concatenated, maybe some line numbers got something got changed, because I did some searching. These line numbers are correct in the file. So like there was an aardvark found at line this in that file. Okay. And you can check, like here. That was file 11800. 11800. Okay, there's that file. Now search for aardvark in it. And it's at line, I don't know if you can see it, 668980, which is exactly what this is. So that number is correct, all right? But notice that the total line number is a little bit off compared to over here. Not by a lot, but a little bit. I'm not sure why. It's something probably when the files were concatenated, maybe the some of the files may have had a line ending at the end of them, and some of them may not have had line endings at the end of them. So sometimes when you concatenated 2 files together, the last line of one file may have been merged with the first line of a next file, and then you lose a line number, so to speak. See, that's where cleaning the data gets really messy. When if some of these files, if you open one of them,
You could be counting carriage returns.
well, that's another
As
problem.
new
Well,
lines?
I tried to clean them up like that. See how this file ends with a couple blank lines? If you
Yeah.
do that, that file does not end with a blank line. So now if you concatenate this file with another file, this last line of this file will be the beginning of the first. It'll merge with the first line of the next file because there's no line ending at the end of this file. That can cause all kinds of weird issues when you're trying to concatenate things together. That's the better way to have, see, that way the file has a line ending at the end of the file. So if I concatenate this file with another file, that line will be by itself. But if I do that, that line actually now becomes merged with the first line of the next file. Okay? And so I'll give you an example of a quirkiness of this. By definition, every C program must end in a line like that. It is wrong to write a C program that's like that. And that's because when you have to merge C programs together in like include files, all kinds of things go wrong if you start merging files together and they don't have new lines at the end of them. So it is technically incorrect to have a C file that doesn't end with a line like this. Okay, it is technically incorrect to have a C file where the last character of the file is not /n. Okay, so I got a feeling that's what's causing my line numbers not to quite agree in the case. They're not off by a lot. If you compare the line numbers in the big file with the line numbers when you go through the files one by one, they're only off by a small number, which means I think that some of the files were, some lines got lost because 2 files kind of blurred together from end to end. These line numbers are always exactly right. If you look in any one, if you look up in that file where an aardvark is, it'll be at that line number. So the line numbers are correct within the files, but they probably got a little bit messed, and these line numbers are correct within the big data file. but the merging somehow, some lines were lost. Okay, but notice that we're now processing 1,000 files in serial, not in parallel yet. But if anything, there's no slowdown in anything, which really did surprise me. Okay, I don't know if that means that this little trickery up here is actually very, very well written. Yeah, it might actually be that we'd have to write this in more. It'd be interesting to write this in a more old-fashioned style of Java using the older Java libraries and see if it does change the speed. Maybe the older libraries don't work as well as this library did. I have no idea if this is just really an improved if this thing here that collects all these paths and then iterates through them, maybe it's just extremely efficient. I have a feeling that this library is not all that much better than the old library. So I bet if we rewrote this in the traditional Java way, it would be just as fast. I think it may just be that the Java libraries are very good at opening lots of files. Okay, all right. So now we can read through all the files in order. There's nothing parallel here. Okay, and we're reading all the files in it was like 5 or 6 seconds. Okay, so now let's parallelize it. Okay, now I parallelized it one way, and I didn't have time to do it another way. So let me show you what I did. Okay, so here was this is the one we did in class the other day. This is the fast parallel search of the one big file. Okay, so this is the parallel search of the big file. Okay, 4 seconds. Oh yeah, it's faster in the serial search, not by a lot. Remember, because of our analysis, we don't actually get the advantage of more than two couple cores, because we've got the I/O part and the serial part just about balanced. In this analysis, where's the right here. In this, we're in this situation where the I/O operation takes about the same amount of time as the serial operation as the task. So these guys are about balanced. So you could have one core do this while one core does that, and there's no need for another core. There would be no other work for another core. And that turns out we saw that. It doesn't, like right now, this thing has been, I gave it 12 cores, and if I take away almost all those cores, it's going to run the exact same speed. It really wasn't using 12 cores. Okay, and we know that from the analysis that, see, it ran in almost exactly this. This one time it ran a tiny bit slower. That might be that it could have used maybe one more core, or that just may have been a quirk of the. Remember, Zoom is running in the background. Zoom is actually fairly busy in the background, so all the timing information is a little bit suspect because Zoom is using a reasonable amount of CPU time, a little bit, and it might even be using it on multiple threads, but Zoom is busy. It's page faulting a fair amount, so it's doing its own I. So the Zoom is actually hitting the hard drive reasonably well, so Zoom is page faulting fair amount, and it's using a reasonable amount of 5% of CPU, 6% of CPU. So timing from one run to another with something like Zoom in the background is going to make it, the timing isn't going to be super consistent. Okay.
Did you still want to try my version of it?
I did. Your version is this version. Yeah, I worked. I didn't have time to send it back to you. I went through your version. It is this version. It is exactly.
Oh.
It is exactly what it's exactly what we're doing here. When I looked at it and I kind of rearranged the code a little bit, it was almost 1-to-1 equivalent to this. Okay, so it was essentially this code here. Okay, Like you weren't, yeah, it turned out to be, it actually was shorter than this code. It was fewer lines of code, but logically it was exactly this thing here. And it took exactly the same amount of time because it was exactly the same thing here. Okay. Yeah.
I thought it'd run faster on your computer because you have both a newer CPU, a better.
It ran as fast as this one
SSD.
did. It ran the same because it was essentially this code here. Just
And
it
you
was,
also have a clock speed literally double of what I
yeah.
was running on the cloud server.
Yeah, it ran in, well, I think it ran in a little over 3 seconds. So this one's running in just over 4 seconds, but I was doing it without Zoom in the background. I think it ran in just over 3 seconds. So maybe it was a little bit faster. It might, but it was essentially the same structure. It was the same piece of code.
The big difference I see immediately is that I'm grabbing a much, much bigger buffer from the disk.
There's a lot to play around with to see if the buffer size could make things faster. Yeah.
I'm grabbing double that.
Yeah, and it that's a good. See, there's all kinds of little things that can affect the speed of these programs. Like we got from a program that took several minutes running on all our cores, which, if you think about the other, we wrote a lot of parallel versions. Some of them were just ridiculously slow, but they used all the cores. This one got to where it's the right structure, but there still are things you could tweak in it, like the buffer size. Maybe there's an optimal buffer size to make this thing run a little bit faster. I haven't had time to really play around with the different buffer sizes. I don't know if there's anything else besides the buffer size that you could really play around with in this program. The executor, like the number of threads is not, the number of cores in the thread pool probably is going to have almost no difference. Yeah, I don't know if there's really, other than the buffer size, there may not be much else to play around with. Okay. All right. So there's the parallel program on one big, huge file. Okay. Now I did the same thing we did a minute ago to make this work on the little files. I just turned this main method into a search method. Okay, let me show you what the code looks like. And then just oh, wrong folder. Go back to the folder with all the, there's the folder with 1,000 files in it. There's the two parallel programs. Okay. This is the parallel one on one big file. No, yeah. There's the parallel one on one big file. Okay, here's the parallel one on lots of files. So it's going to do the same structure. It's going to, the main method is going to get this stream of files. Oh, but the main method, okay, the main method is going to get the stream of files, filter it, and then for each file, call the search program, the search method. The search method is where the parallel is now. So there's no parallel here. I'm not parallelizing over the files, and that's actually what I should do next, but I didn't have time to. What I'm doing is I'm parallelizing within each file. So this is still the same parallel program that was used here to parallelize the search of a massive file. What I'm doing now is parallelizing the search of each individual file. So each one of these files is searched in parallel, but then so I search that file in parallel, then I search that file in parallel, then I search that file in parallel. So I'm serial across the files, but parallel within the file. And now, so that means it might still be able to make this go faster by also parallelizing across the files. But that's where I ran out of time. So here, this is, so the main method gets the list of files and sequentially goes through the list of files and searches one file. And it will not search the next file until the search of this file returns. So it's a sequential search over each file. But each file is searched in parallel. So each file does the process of when it has a buffer, it reads data into the buffer, and then as soon as the buffer is full, it forks a worker task on that buffer, then it reads another buffer and forks a worker task on that buffer. Okay, so each file is parallelly searched, but there's no searching in parallel across the files. Okay, right? Now, you can run this. And it's fast, you know, it's about, okay, here's the parallel search in one big file. There's parallel search in one big file. And here's 1,000 parallel searches in 1,000 files. Okay, and the time, well, actually, this one was faster. I don't know if that's going to be consistent. Actually, it was quite a bit faster this time.
Yeah, whole second.
Yeah, a whole second. That's actually 25% faster. Yeah, this stuff is endlessly mind-boggling. You almost have no way of figuring out that everything you think is going to be true turns out to be different. Like I thought reading 1,000 files was going to be a problem, and it's turning out to be too easy. Even I was able to write this code last night pretty quickly in the middle of the night, and I was surprised that I didn't just hit a brick wall. It went through these files. You can see that it went through each file. It found aardvarks in each file. Found them in different line numbers in each file. A lot of the aardvarks were in this one file. There was actually one file that had most of the aardvarks. Now you can.
Looks like a thesaurus.
Yeah, it was a thesaurus. Yeah, there was one file in the directory that happened to have been a thesaurus, and so it seemed to have had a whole lot of, for some reason, there's a whole lot of instances of the word aardvark in one file, and this file had 2 aardvarks in it. This one had 1, 1, 1, 1, 1, 1, then a whole bunch in one file. Okay, so just this weird. I don't even know. I picked the word aardvark just out of the blue, and it turned out to be a good choice. It wasn't like searching the word "the," which would have bazillions of it. So it turned out but it wasn't a word that had almost no answers. It turned out to be kind of an interesting word to have chosen for some odd reason. Okay, all right, but it turned out to be really fast. Now the next question is, what happens if I parallelize over the files? Once I have remember each parallel search is only using 2 cores, because this guy, the way it's written, one buffer full is about the amount it takes about as much time to read a buffer it takes to process a buffer. So there's really no need to have a separate thread. But on the other hand, why can't 2 threads be doing one file? Clearly I should be able to have 2 threads reading that file in parallel, while 2 more threads are reading that file in parallel, while 2 more threads are reading that file in parallel. I've got 12 cores. I should be able to read 4 or 5 files in parallel at once. So, but I'm not even sure how to do that. I'm actually, last night, this is where I ran out of time. I was now, the next step, now, right now, this is kind of the bottleneck. This guy is serializing the calls to search, because it's pulling out, it's creating this stream and then pulling one file out of it, pulling one file at a time out of the stream. Okay, so in this case, now there are such things as parallel streams. I don't know if this for each can be parallelized. I think it can. That was one thing. I think there is a parallel for each that would essentially say that these are independent operations. So why not? They don't have to be done in sequence. So I think there's a way to turn this stream code into parallel stream code. It might even be as simple as one. This is where. Let me Google something. Java. Okay, see, like here, for each loop versus stream for each. We're using the stream for each. What I want to do is see, can we switch to a parallel stream for each? So maybe this thing will say real quick just what can be done. I'm trying to look up what the syntax is for a parallel for each stream. See if there's, I can see.
That's not it. That's not parallel.
Pardon me?
I thought that was the parallel one at first, but it's not.
No, yeah, this is still, there's a stream for each. So there's not, let's see. There.
Parallel.
Oh, parallel stream. Let's see. Okay, let's try. I don't know if this will work. If we can turn our stream into a parallel stream. Let's try converting it right there. Okay. Before the, I don't know, I don't even know where the, let's see. Doesn't like that. Oh, wait a minute.
Front of the for each.
Yeah, so that might have been the wrong place to put it. So let's try putting it after the for. Yeah, after the filter, before the for each.
Well, we need to import the library.
Oh, did I not have the import for that one?
Good call.
Which one do I need to import? Because I'm importing, yeah, okay. I'm
just doing all the utils.
yeah, just, I don't know if it's put something in there. No, that wasn't it. I'm probably using the wrong streams. It's been a while since I read about the, let's just try, let's just see, let's just kind of randomly go through and just try putting this two parallel stream see if it's, if it's accepted somewhere in our stream, in our pipeline. So we've got this pipeline. Could try putting it there. It may not work in this pipeline. We may have to set up the pipeline in a different way.
I found an example too that just has parallel instead of parallel stream. Well,
Yeah, I wonder if they, yeah, maybe there was some, yeah, just dot parallel.
yeah. I don't know.
Yes. Yeah. 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 That's the trouble with, there's a lot of messed up code in the internet. Okay. Who knows? Okay. I wonder if it matters where I put it. Let me move it around. See if it can be, can you parallel because we actually want to parallelize it just before the for each. That would seem to make the most sense. Okay. Okay, it didn't crash.
Right.
Yeah, did it actually run faster or not? Let's see. Yeah, is there any evidence that it was? Let's see. Now,
I forgot what the last time was.
yeah, it was the sequential one. I'm sorry, the parallel on the huge data file was, well, that's where it was. It did speed it up a little bit. Okay, here.
Yeah. Half a
I've
second.
lost my note. Okay, so let's run it a couple times again. Okay, it's real easy to switch. No parallel. Compile. Run. Go ahead and run it one more time. There's 2 runs without the parallel keyboard. Okay, now put parallel back in, switch it to a parallel stream. Let's run it a couple times.
Oh, that one took longer.
No, pretty inconsistent. Like
Yeah.
this one, they're running at about the same speed. See, this one was 3,200. This one was 3,200. This one was 3,300. This was 3,400. So they're basically just randomly, they're essentially equal speeds. Okay, so that parallel thing didn't speed it up. Now I don't even know if it really, but I don't know if it did what we wanted it to. Did it really do what we wanted it to do? We're just throwing that word parallel in there may not have actually done it. It's supposed to turn your stream into a parallel stream, but I don't know a lot about Java's parallel streams. I do know that there's some controversy over them. They don't always work as well as people. The library, they seem to be kind of not a success. They work well in certain situations, but they don't work as well as people had hoped they would. So it could very well be that throwing in dot parallel here doesn't really help us at all. It didn't help us. We should be able to parallel.
I said right.
Well, it didn't help us, though. It should help us. So maybe we need to break this thing up and do it rather than might have to do this by pulling it apart and doing our own scheduling of essentially opening a file and running it on one core while we open another, calling this method in parallel on multiple of files at once. I wonder, let's see. Yeah, offhand, that's the next thing to do. And that's going to take a little bit of work, I think. Yeah, because this, right now, this is essentially inherently serial, except it's got this guy here. Okay, but without him, it's serial. With him, I'm not really sure what it's doing. Okay, like this, it's inherently serial. Like this, it's hard to know exactly what it's doing. It's supposedly parallelizing the stream, but is it really parallelizing it in a good way or not? Okay, it may not be parallelizing it in a particularly effective way that helps us. We may have to parallelize this part ourselves. I may have to figure out a way to do that. And now we could, at that point, it's not even clear whether it's worth parallelizing over one file or not. These files aren't all that big. Yeah, is it a good idea to, if you can parallelize across files, do you still need to run it in parallel within a file? Okay, because running it parallel within a file didn't actually speed things up a whole lot. Well, yeah, it did. So maybe, maybe it is worth parallelizing it both two ways, parallelizing it across the files and parallelizing it within a file. Because, that parallelizes the I/O within the file. So, I think we still want to parallelize it within a file, just like we're doing here, but we definitely would like to parallelize it across files here. Okay? But I don't know, okay, so offhand, I'm not sure exactly how to do that. Okay, but the interesting thing is just how much this is an easy problem. This is not a deep problem. You have a whole bunch of files, you got a word, you want to find that word in every one of the files. Okay, that's not a mind-blowing abstract problem. Okay, but it's turning out to be kind of tricky to find the right way to parallelize it. And I keep pointing out that when I look at textbooks, I'm kind of disappointed. They tend to pick some silly problem. Actually, this is kind of a silly problem, but they pick a problem that's even sillier than this and then they parallelize it. They use all the cores, but they never show you that they've ever accomplished something. They never throw their code at a huge data set and say, look, it really did speed up. So as soon as we start throwing our code at really big data sets, we start realizing how tricky it is to actually get speed up. It's trivial to get all your cores busy. And one of the ironies here is the fastest version of this program didn't use multiple cores. It used only 2 or 3 cores. When we actually had a parallel programming running on all 12 cores, it was dog slow. So it takes real analysis, real thinking about what's going on to get things to be fast. You can't just say I wrote parallel code, so it must be fast. And that's where the books just don't. They show you how to write parallel code, and I've seen very few that actually go into the nitty-gritty of saying, okay, what's going to happen when we actually try to run it on a really big data set and see where we really do want to get speed up. We really do want to process all the files in this directory as quickly as possible.
One of the big problems that we might be having here is that text searching is a linear time algorithm. What if we tried something that's n squared?
Well, it would no, because parallelizing it doesn't make it anything. It's still n squared. Parallelizing.
Yeah, but 8 times faster is still 8 times faster.
I'm not sure what you mean by 8 times faster.
If you have 8 cores and you can get good scaling, 8 times faster is still 8 times faster.
That's true with linear algorithms too.
What I'm saying is that the fact that it's linear and we're pulling stuff out of I/O means that we're probably just hitting I/O bottlenecks.
Well, that's what we're trying
Whereas
to
with an n squared algorithm, we might be hitting CPU bottlenecks instead.
Well, I/O bottlenecks are where the hard problem is. So we're actually attacking the meat of the problem here. So this is where the hard stuff is. So that's why I'm kind of sticking with this. What you're saying is, let's switch to let's switch to something that's easy to parallelize. So like an n squared algorithm over like a big 2-dimensional array. And then it's, that's the part that's actually usually not that hard to do. This is what's hard to do, to parallelize over a combination of I/O and compute. And I think that this is the hard problem that's worth doing and worth trying to struggle with. This is hard, and we are, you're right. The problem we're having is that it's hard to parallelize over I/O combined with compute. Now we succeeded, we've done it. We started off with something that ran much slower than what we've got now. We've got something we're down to 3 seconds when we started off with something that took a couple minutes. Okay, so we have accomplished a lot of parallelizing, okay? But it's a struggle. And we might still be able to parallelize some more. We may be able to get this thing down from 3 seconds down to 1 or 2 seconds. I'm not sure how much we can squeeze out of it if we parallelize across these files. I'm kind of curious to see what we can do. But parallelizing across a combination of I/O and CPU bound is the hard part. So yeah, that's why we're struggling, because we're trying to do the hardest thing. Yeah.
What I was going to suggest is a more useful operation that's still pulling I/O predominantly, which would be the table function.
The what function?
The table function. So you take the book as an input, and you do a tabulation. You find out how many times does the word "the" appear, how many times the word "aardvark" appears, and you make a table of that.
Mm-hmm.
And best I can tell, that's best case scenario n squared or log n
But that's
squared.
just running this program several times. That would just be, I mean, this program is doing the aardvarks, and then if you want to do another word, you just, you would just, it's just this program over and over again. So it wouldn't change the algorithm in any way. This would just be one step in that table. This would give you one row of the table. Then you do it again to do the next row of the table. This one does aardvark. This one does aardvark, and then you do it again with elephant. Yeah, and you kind of, so that would still be this problem over and over again. It wouldn't. It is an n squared algorithm because you have to do this linear operation on every word. Yeah, but it doesn't. I don't think that changes what it wouldn't. I don't see how it would change the code we're writing. We would just be iterating this guy over the words in our table. Right now I've hard coded it to do just one word, but it wouldn't be that hard to change this to iterate. Like your code had the word as a parameter, so that was nicer. Yeah, so your code did it nicely with the word as a parameter instead of hard coding the word into it. So I think I'll change this to do it like you did it, with the word as a parameter. But then it's still, then it would just be iterating across all the words, but we would still be, that would just be one more loop outside of this guy that said, okay, let's do each row of the table. But each row of the table would still need to be parallel, it would still need to be, this would still be the amount of work it would take to find the word in all these files. It's just inherently tough to mix I/O with computation, because I/O is a little bit, I/O is just it's I/O is where the, when you're doing I/O, you're talking with the hardware. We don't schedule the I/O. We actually program the computation on the CPU. The I/O is just this. You ask the operating system to do the I/O for you. So that's a blocking operation. So you have to find some way to manage your CPU while you're blocked on the I/O. That's why there's futures, async. The JavaScript. The JavaScript world, the Rust world, the Java world, they're all struggling with trying to find the best way to do, kind of like what we're doing here, okay? Thread pools, futures, async await. There's a whole new, right now, there's something called coroutines. That's another design pattern that's starting to become popular. We've been looking at futures and some asynchronous I/O, but people are now saying that even that's not working as well as they wish it did. And there was an article I was looking at the other day. See if I find it. Here. Oh, that's not the article itself. Okay. There's something called Project Loom, which is an ongoing project to change the Java compiler. to add these coroutines to the Java compiler. And that's when that happens, this one guy is speculating that there won't be any real reason to have futures left anymore. So he's not sure, but futures were this thing added to Java recently to try to solve this I/O problem and parallelizing problem. And already people are starting to wonder if futures is really the right idea. So now there's this new project Loom, which is based more on coroutines. And it's another big, hairy problem. Coroutines are kind of tricky. Coroutines are not a trivial matter to think about. And Project Loom is an attempt to try to make coroutines work make it easier for programmers to use coroutines. It's an attempt to try to make these things called continuations and coroutines. Okay, continuations are another idea that came out of functional programming. Continuations are another one of these complicated abstractions that came out of the functional programming world that are trying to see if they can move into the Java world. So Project Loom is trying to add continuations and coroutines. And because what the problem is, what we're trying to see, we're seeing it here. When you try to interleave I/O with computation and you want it to be as fast as possible, it's not so easy to do. Interleaving computation with computation is not hard. You just chop your problem up into multiple threads and just run each thread on a different core. What's challenging is to interleave your I/O with your computations. Okay, that's not so easy to do. So we kind of bit off the hard problem here. The hard, we inherently doing something that's I/O combined with computation, and it is hard. And we've been looking at using thread pools. Like this one doesn't use futures, but earlier we did a combination of thread pools with futures, and now people are thinking that maybe the best thing is to use coroutines. Okay, so it's in a course like this, my goal is to just try different things, look at what's out there, and you won't find textbooks about this stuff. It's all kind of in flux. What's added to the Java library last year, may turn out not to be the thing that people really are going to be using a few years from now. So it's in Java, C++, Rust, JavaScript, they're all going through this process now of playing with futures, async, await, coroutines, futures, thread pools. All of them are trying to find. Another example is the Go programming language. The Go programming language has tried to build this stuff natively into the language. Something called there's a nice pun here. There's this idea of coroutines. The Go people, they built into the language Go routines. Go routines are Go's way to try to make coroutines manageable. That was a cute pun. I don't know which came first, the name of the language, Go, or the idea that we want a pun on coroutine, so let's call the language Go so we can probably the pun came later. But Go has this thing, these things built into the language called Go routines. They are kind of built on the idea of coroutines and their attempt to try to make concurrent programming simpler. Okay, and it's still an ongoing debate whether the Go routines in Go are a good idea or not. Some people think they're a wonderful idea, and some people think they're okay, but they're not as great as some other people think they are. Go routines are kind of unique to Go, but what they're there for is to try to make this stuff we're doing here work. How to combine I/O, thread pools, futures. How do you make this stuff easy to manage? And how do you make this stuff easy to think about? Okay, because right now it's not so easy to manage. It's not so easy to think about. It's real easy to write. It's real easy to write code that looks good and runs terribly. Yeah, it's too easy here to write code that looks like it's the right thing, and then you find out it's slower. The parallel program running on 12 cores is slower than the single-threaded program running on 1 core. Okay, it's real easy to do that in this world. Okay, the Go is trying to avoid that. Go wants it so that if you write a program, if you write it the right way, it'll run fast. In Java world, if you write a program, nobody knows what the right way is. You write a program that looks like it's the right way, and it's ridiculously slow. What signals to you that you were really not writing it the right way, other than to find out that it's slower than a serial program? We shouldn't have that kind of stuff. We should have languages and libraries where if you write things the right way, you've got fast code. But we don't have that right now. If you're real experienced, you probably get a sense of what's right and what's wrong. But you can easily write things that look like they're right, but aren't really right, in the sense that they perform poorly. They're logically correct. They'll be logically correct, but their performance will be really bad. Okay, so yeah, but what makes it hard, for the most part, is I/O mixed with. It's the I/O that's really caught, because you kind of lose control over things when as soon as you ask the operating system to do some I/O for you, you don't know when it's going to be done, and you don't really. And another place where this happens is with networking programming. Like a lot of this is motivated. I've mentioned this before. When you load these huge pages, and these pages just have gazillions of things going on. See, look at all the things that are happening in parallel while that page is loading. Okay, that's a hard thing to code. You don't just load this image, then when it's done, you load this image, then when it's done, you load, the people who wrote this page had to load all these images simultaneously and had to worry about the fact that one of them might die on them. Remember, there's this idea that one of those images that something might go wrong with the network connection from that one image. So, that's a big part of what's motivating this, is there's I/O mixed with computation, mixed with failure. We're not even throwing in the failure here. None of these files are going to fail on us. But in the real world, that's actually what becomes hard, is they're mixing I/O. The I/O is loading all these things. The computation would be the browser has to lay out everything. There's a lot of calculation to do where the browser has to do a lot of calculations on layouts and stuff like that. And then there's the problem of failure. Okay? There's all kinds of things that any one of these images could fail to load, and maybe need to be retried or things like that. So there's all kinds of things that can go wrong. So that's one of the things that people are trying to deal with. We're just seeing I/O mixed with computation. That's hard enough. Then mix in failure. So with failure, you'd have to somehow be able to say, oh, one of my calculations failed. Should I restart it? What do I do with the data I've accumulated so far? Do I throw it away, or can I somehow restart the calculation in the middle? But so I/O mixed with calculation, mixed with failure, you end up with some pretty complicated code. We're only doing I/O with I/O and calculation mixed together. This is where all these techniques are trying to get at, try to make it easier for people to manage this kind of stuff. Okay, so so the last thing we'll do is maybe today's Wednesday already. If you can, if you can find, like, there's a concrete little problem here. We've got this guy. We've got 1,000 files here. We've got parallelization across any one of these files, and we've got, well, we don't know if this is really parallelizing or not, but we should be able to parallelize this thing over files. See, if any of you can find something that you think would be worthwhile, that would be interesting, how to parallelize this part here. Probably this stuff here won't change. The search within a file is probably parallelized reasonably well here, but clearly this part ought to be parallelized. So see if you try that. Look, see if you can find something over the next few days that would do that. Okay. Look, I don't know if this thing can be made to work better, or if it's just going to have to break this up and just get rid of the stream. Maybe we'll need to do a thread. There could be another thread pool here. We could do over this collection of paths exactly what we do here over this collection of lines. So it may be a matter of throwing these guys in a thread pool. It may have nothing to do with using the stream operation. Okay, so we've run out of time. So if you have questions, write to me, and please look at that code. I think it's interesting code. Please look at the code and see if you can come up with a way of parallelizing that last step, parallelizing over all the 1,000 files. Oh, and I'll put the 1,000 files up on the website. I'll zip them up so you have exactly the same data that I have to work with. Okay, so I'll end here. Bye.
Bye.